has two purposes. The first purpose is to define the traction force properly. Second purpose is to actually help to define a certain term that could help you understand the determinant part of the principal stress. It's actually not very much related, but I just want to show you that this is related as a little bit. Traction force is a force acting perpendicular. It is definitely perpendicular now, alright? And we have a body. If there is a traction force, this means that it's perpendicular to that particular surface of that body. That's just the meaning of that. And this traction force is a normal force, alright? Therefore, it's denoted by N over here. And if you're talking about 3D, because N can be, if it's 3D, you have a 3D traction force. All are normal forces, right? If you remember, sigma 1, 1, sigma 2, 2, and sigma 3, 3. Some sort of that. Okay, so far so good. But now, and therefore, we will actually write it as sigma. This is actually some constant that can multiply with our nj, which is a 3 times 1 vector. Because it's 3D, we will have a tj, which is also a 3 times 1 traction force. Some sort of the meaning. Okay. Next video, we'll actually do something in terms of principal stress, as I say. And principal stress means that you're going to take a tensor, a stress tensor, and you're going to multiply. You're going to multiply by a so-called a vector. Well, however, this is a vector. How can you multiply a 3 times 1 vector with a 3 times 3 matrix? You can't do that. So what can we do about it? Because at the later part of that next video, alright, we actually ignore the understanding that this is actually a vector, because what we do is simply sigma 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 0 0 0 0. Alright, and we minus away, and this is one form of a solution to actually solve for this one, right? Because you want to minus away this vector. How can you transform this vector into a matrix? And therefore, this is the purpose of me here right now, to actually share with you that particular understanding. Alright, and also that in fact there must be a certain nj. Never mind, I'll just derive for you first. Later on you'll get what I mean. Alright, do take note that the stress symmetry over here is 1 2, this is 1 3, and this is 2 3. Alright, because it's a stress tensor, so therefore it's a symmetry system. But it doesn't apply much to what we're going to say right now. The stress tensor can be expressed in this, alright, because if you were to, this is 3 times 3, this is a 3 times 1, which is what we have shown if you were to multiply, alright, if this cancel out, if you were to multiply, in other words, okay, I didn't have, so instead of this sigma as a constant, we can actually build it out into a 3 times 3 matrix. Alright, and an nj. Alright, and we have, in other words, a sigma ji is equals to ti. This should be I in this case then. Right, because j has become a dummy indices. Alright, it shouldn't cancel away this j, because this system, this tj, this traction force, is different from this ti traction force if you take a look. Why? This is in the j basis vector, this is in the I basis vector. They are totally two different stuff. Alright? And later on you'll know that this j, alright, is the principal stress. Alright, because it is in a different basis. While this ti is the stress tensor that we always talk about, sigma 1 1 etc. Alright? So later on you'll get to know how the things would go. Alright, for this is just, take note that this is just a simple 3 times 1 multiplied with a constant only. Alright, so what we have been doing now is to actually show you the certain trend, alright, so that you can actually understand. So therefore now I'm gonna take this thing, since they are in a different space, but I want to minus them together. I see some relationship between them. Alright, so therefore I take this, alright, this is sigma nj, I paste it over here. Sigma nj, and this ti, I can actually paste this thing over here, like sigma ji and nj. Okay, how I derive this thing over here. Okay, except that I actually should have write J over here. Okay, because it's this one. Right, I actually didn't see properly. Now, if you take a look, this NJ, alright, this traction force and this traction force are the same, but this traction force are acting in a different basis. Okay, so this traction force is acting on a different basis. If I say this is the basis, alright, this traction force is acting on perhaps on the J basis, alright, maybe an I basis. This whole thing is, so this normal force is acting in the J basis, while you're analyzing things, maybe looking at the I basis, and therefore this is the traction force in terms of the I basis. Right, so you're actually translating all this information into the I basis or something like that, or you're gonna relate them all together. But I just don't want to confuse things. Alright, it's really quite confusing. I've somewhat shown you a piece and parcel of how this is being derived, alright, in terms of the spatial configuration. But now it's all still go back to, because this is a vector, you cannot minus it with a matrix. Right, this is 3 times 3, this is 3 times 1. You cannot minus. And therefore, how do we do this? Is to simply multiply with a canonical ij, nj. Alright, so we have served the purpose, because canonical ij will create an identity matrix. Okay, because when I is equals to j, it is equals to 1. When I is not equals to j, it is equals to 0. Alright, so therefore, and for this system, right, I and j is equals, if I is not equals to j, is equals to 0. So this is why these three are all equals to 0, because they are not the same as each other. This is actually 2 1, right, 2 1. So left out we only have 1 1 1 over here, which is the identity matrix, and therefore you can actually translate it to a matrix itself. And since I can re-represent this system, alright, as this system, simply rewrite the formula as this, alright, with this minus sign equals to 0. Alright, and then we will factorize out the nj because they are the common terms. So I have j sigma I minus sigma delta ij, and nj is equals to 0. So I actually group everything into the j basis now, in the j space. So when we solve the answer, we're actually solving for the j space. Okay, and later on in the next video, you'll know that we are gonna get a determinant of this matrix. Alright, when this one, because this is a 3 by 3 matrix, this is a 3 by 3 matrix. When you minus, you'll still get back a 3 by 3 matrix, and then when you get a determinant and solve for things, you'll be there. But however, because in the next video we're always focusing on this thing that I actually forgot nj. In fact, I don't know what is nj, by the way. So therefore, after that particular week, now this week, I realized that nj is being derived in this manner, and this nj is simply the traction force that is acting on the perpendicularly to the surface of the body. And I shall see you in the next video for the principal stress. See you there.